introductions about ourselves. Introduction, your name, where you're joining in from. Oh, Simon Novaga. Oh, Norbert, you're welcome. Joining in from Abuja, Nigeria. We'll be starting in about 2 minutes. And if you notice that you're not joining in with your own name, please go ahead and change the name. You can just go to your name and where the participant list is, click it and rename yourself and put your name. Oh, Winner, I see you. Thank you so much for joining. He's joining from Nigeria as well. Yeah, I think we can start now, and we'll just keep making the publicity that the event has started as we go on. Thank you so much for joining, Mrs. Chidima. She's joining from Port Harcourt. Shout out to you. Good morning, good afternoon, and good evening to everyone, wherever you're joining in from. My name is Ibo Shalom Chilaro. I'm the founder of Renewable Technologies, and it's my pleasure to welcome you today to our first edition of Renew Education Program. And we have a simple goal with this initiative. And I'll just tell you a little bit about Renewable Technologies, and we'll go ahead to dive into the section today. Renewable Technologies was founded in 2022, and it was founded to promote climate change awareness and advocacy, access to clean. Sorry about that. Okay. It was founded in 2022, and it promotes climate change awareness and advocacy. It provides access to clean and affordable energy and equips young people with renewable energy designing skills for a sustainable energy transition. And our mission is simple, is to reach out to the undeserved and marginalized areas of Nigeria. And to achieve our goals, we organize renewable energy awareness campaigns. We design literary programs and curriculums, and we provide as much as we can technologies to empower youth and students in local communities, schools, and people at the grassroots level. This special initiative is termed Renew Education, and it's a monthly education series that is designed to equip young energy leaders, enthusiasts, and professionals with the right knowledge to explore future renewable energy careers. And as the educational series unfolds, we will be onboarding proficient energy leaders to drive renewable energy knowledge within their communities. So it's my way of telling you to look out into your emails and into just look forward to the call of application, because we'll be doing that at the end of February. And our goal is simple. We seek to prepare a competent workforce resilient towards promoting the renewable energy transition and fulfilling the United Nations Sustainable Development Goals 4, 7, and 13. So this is the plan of the Energy Leader Scheme. The Energy Leader Scheme is a scheme, just like I mentioned, to train and equip young energy leaders, and they will serve as a channel through which our organization accelerates its goal of renewable energy education. So we have 2 stages, and energy education that the volunteers will be involved in. The first is to renew schools. So renew schools is a terminology used for climate change and renewable energy advocacy in schools. And renew communities, it's a term that it's used to renew your communities, your closest place. It could be like your market, it could be the companies, it could be anywhere. It could just be your local community, it could be your village, it could be anything. But the basic idea is that it's not a school, it's within the community. And the qualifications are not difficult, because we are seeking to empower both entry-level and mid-level energy enthusiasts and leaders. So the qualifications are quite simple. We have that the first we want you to do is to be able to attend all our education webinars with evidence of attendance. You can take pictures. You can just send me an email. You can send me a note. I attended this section just to keep your attendance records. And the second is that you have to possess a commitment to grassroots mobilization and education. And finally, you have to commit to all outdoor activities as designed by renewable technologies. And these outdoor activities, you will learn further about it when the call of application is out. The first is going to be happening in March, the second in June, the next one in September, and the final one in November. What are the benefits of engaging in this Energy Leaders Scheme? The first is that you gain experience in climate and renewable energy advocacy, because we have a curriculum that we're going to be sharing with you, and some renewable energy materials, including topics in climate change, in leadership, in youth action that we'll be sharing with you. So you'll be gaining experience across these levels, and then you'll also be able to enrich your networking, your communications, and your leadership skills. You'll be able to engage in peer-to-peer education because you'll be interacting with all the other volunteers and educators. And finally, there will be a little project reimbursement and stipend for anyone that is being selected to join this initiative. And if you have any further questions or inquiries about this initiative, and possibly you want to keep up to date to when it's going to be shared, please send me an email at that email address, or you can just send me a message at any platform that you saw this link, and I'll be able to take it from there. And now it's my pleasure to welcome our highly esteemed professional that will be taking on our first course today. He is Dr. Muiz Agbaje. So Dr. Muiz, over to you.
Thank you very much, Shalom. I believe everyone can hear me clearly.
Yes.
Oh, great. So my name is Muiz Agbaje, as she mentioned. I'm actually a PhD student here at Rensselaer Polytechnic Institute in New York, United States here. So I'm currently working on integrated energy systems, particularly with relation to nuclear energy systems and hydrogen energy systems. So my research generally focuses around integrating hydrogen systems like solid oxide electrolyzers with nuclear energy systems to generate, for cogeneration, basically generate both heat, electricity, and hydrogen. So, and I think that's why Shalom felt I'm qualified to give this talk today. So I'll try to do justice to what integrated energy systems mean for a clean energy future. So I'll go ahead and share my screen now. Yeah, I believe my screen should be visible now.
Yeah.
Okay, thank you. Yes, so let me go ahead and start. I think we've waited quite long enough. I don't want to waste much time. So if just a few things before I start my presentation. If anyone has a question during the presentation, you could type in the chat box or you could raise your hand. I'll take the question. And so that you don't forget as we go ahead. I'm very fine with, stopping in between and answering questions. It's not that much of a big deal. I believe the idea is for everyone to learn. So the better we learn, the more successful this program is. So to the presentation proper, as we all know, this is why we are here, to learn, to understand how integrated energy system works in a clean energy future. So in today's presentation, I would try to, give some background into what energy consumption is. Why do we need clean energy in the world today? So I'll talk about integrated energy systems. Why do we need it? Why is it important that we integrate our energy systems together? Why do we have to add 2-3 systems together? And what are the parts of the system? How do we say an energy system is integrated? Do we just put two things together and say, yes, we have integrated? Well, what are the requirements for integrating energy systems in the context of clean energy, to be precise? Because we could have other types of energy systems that are not clean and still be integrated. But my focus today will be in the context of clean energy. Then I'll give some examples of what it actually looks like. And then I'll give like 2 examples of systems that are currently in use, like practical systems that are in use. And then the challenge is why, if it is so good, why isn't everyone using it? What is the drawback in integrated energy systems? What are people facing? What are the challenges we are facing? Then some policies and regulations supporting that. Then what the future looks like. And then finally, I'll conclude on today's presentation. So the idea for me, the idea here, what I want to achieve here is to give a high-level information on this topic we are today, and to spark interest in this kind of thing. So if you are an energy enthusiast, you should know that it's not just about solar panels. There are other parts of the system as well that you should take into consideration. And those parts might end up being more interesting for you than the actual, generation system. So I hope this serves as a motivation for people to, delve more into these systems. So as I said I would give some background into what energy is like in today's world. So this is global energy consumption. I believe this data is for 2022. I got the data last year. So we can see that renewable energy, or let me just say clean energy. So clean energy, we characterize it as energy that does not give off greenhouse gas emissions or gives off a very low amount of CO2 to the environment. And by the colors here, you can tell which ones are clean, which ones are not clean. So we have coal, oil, and natural gas. Of course, some people could argue that natural gas is sort of clean energy. But for the context here today, I want to categorize natural gas as a fossil fuel. So coal, oil, and natural gas are fossil fuels that does not contribute to the clean energy we want to talk about today. So that means we have just 18% of global energy consumption from clean energy systems. So that means we still have a lot of work to do, to get these systems to a very large amount, maybe at least 50%, because of what we are fighting, right? Climate change, to reduce the effect of greenhouse gas emissions on the climate change, and to, put a brake on the increasing temperature of the atmosphere. So we see the whole picture here. Why do we want to go for clean energy? This is the reason why. These numbers that we have here. We're not trying to victimize anyone, we are not trying to victimize coal or oil or natural gas, but we are saying we need to do more in terms of clean energy. That's just what we are saying here. Let's do more for clean energy systems based on what we have here. So what are the challenges we are facing in current energy landscape? By energy landscape, I mean what we have now in the world, the energy systems in the world. What are the problems? A lot of energy systems, the transmission distribution system, have been built like 40, 50 years ago. They aren't really new transmission systems. So these things are really old. We need to build new ones, to take care of most of these things have lifespan of like 50, 60 years. So like next 10, 20 years, some of them will start getting out of phase. We have to build new ones. So those are challenges we are facing. Because they are old, and because the technology they use to build this thing are old, there are losses. A lot of losses are being incorporated in the systems, and we need to reduce these losses. Of course, that's due to the age, because it's been a long time. We need to build a new one. So it's aging, they are dilapidating, and there are lots of losses incorporated due to the age of the infrastructure itself and due to the technology used in building it. Also, there's what we call the energy access disparities, which I believe a lot of people from third world or maybe second world countries will understand this. Not everyone has the same level of access to energy. So we have some people have, like, I know some people can relate here. You have energy access, you have like maybe 4 hours of electricity in a day, or maybe 10 hours. So we have these challenges we are facing, and we have to deal with it. How do we deal with it? One of the ways of dealing with it is building infrastructure to exploit capacity in the energy systems. And finally, dependency on fossil fuels. So we already know coal, like I mentioned in the last slide, coal, oil, and natural gas, they have high percentage in the total energy consumption. So we want to reduce this. These are the 4 things that are pushing us towards clean energy, towards more resilient grids, towards energy integration, towards global grid, like we like to call it, where everybody uses energy. So these are the challenges we are facing. Sorry, 1 second.
Eperechi, I've been trying to mute you, but it seems like it's
Okay.
okay.
So moving on. Just to buttress what I've said before, we want to see, I'm trying to, just to give some I'm trying to wet the ground, like we like to say, to let you see why we need this energy, to let you understand what is going on in the world today. When people start talking about climate change and greenhouse gas emissions, they are not just numbers. Not that some people just came up with these things. They are actual data for these things. We have evidences to support that these things are happening. So one of them is the global temperature. Like what is the average temperature globally? So we can see from the 1980s till now, we have a steady increase in global temperature. If
Nothing, nothing. That's no joke. Nothing. I've not seen it.
Okay, Zoom is not talking to me then. So we have a steady increase in global temperatures. So these are the things that are pushing us towards clean energy, right? So we have the large consumption of fossil fuels, which gives us a very large amount of CO2. Then this large amount of CO2 leads to global greenhouse gas. Of course, CO2 is the greenhouse gas emission. Then we have this increasing the temperature, the global temperature. So we have noticed there is definitely an increase in global temperature. There is no doubt about that. Climate change is real. We know that. We've seen a lot of things changing in our weather and other stuff like that. So these numbers are there. The evidences are there. We have to do this. But now, then also to give more insight into the cause of greenhouse gas, 70% of greenhouse gas emissions is from energy. So energy has a lot to do in reducing climate change and reducing greenhouse gas emissions. Of course, people will come and tell you we also have greenhouse gas emissions from agriculture. Yes, it is there, but it's very low. Imagine you reduce energy greenhouse gas emission by 10%, for example, and you reduce agriculture greenhouse gas emission by half. It's almost the same thing. Now think of, you go all the way to half for agriculture, but you just do 10% or maybe 20% in energy, and you already have a large decrease. So that makes you understand how important energy is to achieve to reduce climate change, basically. So we have to work in terms of energy. We energy professionals have a lot to do to reduce these greenhouse gas emission and of course combat climate change. So now to properly what we are here for today, we've talked about why we need to do all these things. We've talked about what is going on and why do we need clean energy? What is the motivation for this? But then the clean energy we are talking about here today, we are talking about integrating these energy systems for the clean future. So what do we mean when we say we are integrating energy systems? What is the ideology behind it? So the idea is you design power plant for more than one thing. You don't design a power plant for just electricity generation. For example, you have a solar PV system, you just use that solar PV for electricity and that's all, have a good day. No, that is not an integrated. Idea behind integrated system is to have multiple energy inputs, multiple users, and multiple storage options. So you have a lot of things coming together. And the good thing about having so many things come together is you use the strength of some to combat the weakness of the other. So when you have a system that is not working at a particular time, you definitely have something else to come to cater for that kind of need. When you have high demand, you have several systems to cover for that high demand. When you have low demand, you have a storage system to take care of the excess energy generated. That is the idea behind integrated energy systems, to have several inputs, several users, several storages. So inputs could be input at the energy sources. You have renewable solar, wind, you have hydropower, you have nuclear, you have geothermal sources, you have several sources. And the end users, we have domestic users like you and I, we have industrial users, we have transportation users, we also have commercial users, and also industrial users like those that use the raw material itself, not even the energy, but the raw material from the systems like the biomass and stuff like that. So you have all these things that you cater for at the same time with just one system. or an integrated system, basically. So the idea is to diversify the sources, and by that, you optimize the efficiency of this system operation. Then you have a decentralized and localized energy production. So you can have an integrated system for a local government or a county, and you solve all the energy needs of the county with just that single system. You don't have to buy energy from outside and stuff like that. And of course, you reduce the environmental impact since you are going for clean, renewable energy sources. And this also helps to use smart technologies like smart controls, smart grids. I'll talk about that later in the presentation. And then, of course, we have the social and economic benefit like job creation and stuff like that. And of course, the main reason for doing it, the reduction in environmental impact, the reduction in greenhouse gas emissions and CO2 production. So why do we want to do integrated energy system? What are the benefits? So I like to summarize my benefit under just these 4 things. These 4 things covers practically everything. You want to improve the energy of the system. You want to enhance the reliability and resilience. You want to reduce greenhouse gas emissions, and you create jobs and other economic benefits. Outside these 4, every other benefit of the system is just related to this. As far as I understand, when you look at it all the way, it boils down to these 4 things. You improve the energy, you improve the efficiency, rather. Everybody that wants energy gets it at the time they want it. Energy you create is not wasted because you have storage systems, you have other users that you can serve. Resilience and reliability. Resilience means the system will withstand anything at any point in time. Reliability means when you want the system, it is there for you. So when you have an integrated grid, or let me say, a well-developed integrated grid will definitely give you this. And of course, greenhouse gas emission reduction, because of the sources we are using clean sources, or let me say, renewable sources, sustainable sources. Yes, we can have people that would argue that, yes, even your solar panels, when you use it or when you create them, you have some CO2 emissions and things. But then when you bring the numbers and you compare the data, okay, yes, we have, if you check the life cycle of this solar panels production, or maybe, yeah, the life cycle, and you look at the numbers, after the entire life cycle, how much CO2 is being created, but compared to maybe typical fossil fuel power plant, look at the life cycle of both, and then you will understand that people that are against clean energy are just looking for excuses not to adopt this technology. But then, as far as the fact remains, clean energy definitely is the future of energy systems, like it or not. So these are the benefits of integrating the systems, improve the efficiency. So yeah, the image, this graph I have here is the EU's ideology of their future energy system. So you can see the previous one and then the future. The previous is just a linear interaction between the source and the user. So you generate electricity, you use it in industry and residential, you generate heat, you use it, you generate fuels or chemicals, you use it. There's a linear interaction. But in the actual future of energy, what we want to have is like a centralized, a circular transaction where systems can interact between each other in both directions. So you have everything in a centralized system. You have energy productions and storage. Everything connects to the energy user. So users can take from wherever they want at any point in time without having to lose at any point in time. That's the idea of the reliability and resilience. And the reliability and resilience of the integrated energy systems. So we've been talking about these systems. What do we see? Like, what makes up integrated energy system? What do we see to say, oh, this guy is or this system is integrated with other systems? So these 4 things also, I like to summarize everything into like big headings. So we have heat and power systems, we have renewable energy sources, we have energy storage and smart grid. So the CHP systems are basically all your energy conversion systems. Say how much energy you can convert, what are your converters, and then your sources, your storage, and your control. So you need a source, you definitely need energy sources. You definitely need energy storage, because when you have excess, somebody has to be there to take that excess. When you don't have enough to supply your end user, somebody has to be there to fill that gap. That is what your storage does. Then your converters, solar, the heat from the sun, we can't use the heat of the sun to power our television. It will not switch it on. So we need converters in terms of, it could be your turbine, it could be your heat engines, it could be any type of converter you could think of in converting energy from one form to the other. The heat from your nuclear, or even the wind, the wind turbine itself is an energy converter, because what you're using is kinetic energy of the wind, and you're converting it into mechanical energy, then convert that mechanical into electrical energy. Then that electrical energy, you can convert it into another thing, maybe hydrogen, or you can convert it back to heat energy, depending on whatever you want to create at any point in time. That is the beauty of the system. So you have several sources, you have your converters that are there to give you whatever you want at any point in time, and you have your storage systems to keep excess that you have. So storage system doesn't have to be batteries alone, because I think a lot of people, when we talk about energy storage, the first thing that comes to mind is a battery. Battery is just one of countless numbers of storage technologies. Batteries are there, and even batteries, there are several types of battery. We have the redox flow batteries, we have our lithium-ion battery, we have the sodium sulfate battery, we have the potassium battery, we have the alkali battery. Those are just batteries. Then we have other type of storage like the pumped hydro, which is just, you just pump water to a very high place, and when you need it, you just let the water flow down back. You have electricity. We also have hydrogen energy storage system, where you just store energy in form of hydrogen and use that hydrogen for whatever you want to use later in the future. We have mechanical storage like flywheel storage. We have thermal storage. You're talking about the phase change materials. You're talking of ice. You're talking of rock bed formations and stuff like that. Several energy storage technologies for whatever use you want to use it for. And then the enabler, which is smart grid and control. If you don't have a control system, all these things you're talking about is just a waste of our time. You cannot have an integrated system without control, because something has to regulate how much is being requested, how much is being given at every point in time. So we've talked about what we mean by integrated systems. We've talked about why we need integrated systems. We've talked about what makes up an integrated system. So to summarize this whole integrated system, these are the parts in the system. You have electricity and heat. That's like the most used form of energy by any end user. You have electricity and heat. So your electricity could be supplied by your solar, by wind, by hydro, or nuclear. Your heat could be supplied by biofuels, nuclear, geothermal, and solar thermal. Then your energy storage technology, like I mentioned before, you have hydrogen storage, you have thermal energy storage, then your converters and your end users. So in a typical integrated energy system, you have these people there, or these constituents. You have electricity in one form or the other. You have heat in one form or the other. You definitely have to store your energy, and you need your converters from one form to the other. So now I want to go into a few examples. I mean, I've been talking all day long, trying to, sell this idea of integrated energy systems to you. But then how do these things work? How do they, how do they move together? How do they cohabitate to give us what we want? So one first example I would like to give is a solar and wind-based integrated energy system. So you have your solar panel, you have your wind turbine. Then you want to use this for integrated energy. You want to use this as an integrated energy system. What are the things you need? So if you look at here, we have our sources here is wind and solar. Then our converter, they are not included here, but it's the converters here would be depending on what we want to have in the end. If we want to have heat and electricity, would have heat engines and heat pumps for our converters here. Then of course, everything has to go through the control systems to manage the system demand and supply, because the load here is just a residential building, so you don't really have much to do in terms of how much you have to send, but then you still have to control what is being sent. And of course, because it is wind and turbine, you can actually control amount of energy that is being generated from the system itself. You can shut off some part of the wind at several times when you have too much. And of course, energy is stored here in batteries and pumped hydro system. So this is a typical pumped hydro system. Oh, sorry, thought you could see my. So yeah, so this is a typical pumped hydro system. You have the lower reservoir here is at a lower height, maybe like at ground level. Then usually we use extinct volcano or maybe just geological formation that you have at a higher point. So what you do is when you want to store energy with this type of system, the same pump pumps the water to this top here to store energy in terms like gravitational storage. You store based on rho GH, potential energy for those who are engineering students here. So this is like a potential energy storage. You store the water here. Then when you need power, you just let the water flow down and drives the turbine. So that point it works at the turbine, then electricity is generated, sent to the control system and sent to the final user. And of course, electrolyzers, I like to include hydrogen in whatever I'm talking about because that's what I do. I've been working on hydrogen systems for about 4 or 5 years now. So it's like, that's like my baby. So I like to talk about it at every point I get. So hydrogen systems, basically, the advantage they have over battery, because they practically do the same work as batteries, they just store energy and that's all. But the advantage hydrogen has over battery is that one, you can use that hydrogen for other things. So if you store energy okay, sorry, I'm just seeing your question, Shalom. Okay, let me just finish this and I'll go back to the CHP. So electrolyzers, yes, hydrogen generation. So in hydrogen generation, you use electricity to create hydrogen. Like, how does that happen? The idea is you send water to the electrolyzer. So there are several ways of hydrogen generation, but personally, I prefer electrolyzers, though there are still a lot of the electrolyzer technologies are still in developmental stage, but it is really promising. I believe that this will be a great game changer because hydrogen could be used as fuel for powering anything, vehicles, houses, and you use it for literally anything. Hydrogen storage is like you're storing your fuel in a tank. It does not finish. It does not deplete over time, which is something battery has. If you charge a battery to 100% and you leave that battery for a long time, when you go back, you will not see 100%, I promise you. You will not see 100% in that battery. It will definitely reduce. But for hydrogen, it will always be there. But of course, provided there's no leak in your tank or anything, that's the good thing about hydrogen. And hydrogen can be stored as gas, can be stored as liquid, depending on how far you want to go with it. And it is a very useful gas in the industry for several applications and several uses. And also hydrogen is the most abundant element in the universe. So you don't want to mess with hydrogen. You want to always have hydrogen. So I believe this hydrogen system is the future of energy storage at least. And the good thing is you can convert it very easily, convert hydrogen to electricity and electricity back to hydrogen using fuel cells and electrolyzers, or you can just burn it like an internal combustion engine and still have electricity. So it's just fun. Regarding CHPs, I think my next slide might be a good way to, talk about it. Yes, I think so. So this is for solar and wind-based integrated energy system. I want to give another example. Sorry, this thing is... Okay, good. So here, this is what I like to call a multi-generation integrated energy system. So we have more than one source of energy, more than one type of energy source. So in the previous one, we have more than one source, solar and wind, but they are both electricity. But here we have more than one type. So combined heat and power systems literally means one system that you can use for heat and electricity conversion. They are converters, right? They don't generate electricity. So an example of multi-generation could be a heat pump, but not exactly the heat pump used here. Let me see. Okay, good. This gas turbine here, yeah, this is a very good example of a CHP, combined heat and power system. So you have fuel sent into it here using biogas here. Do we have a question? Okay, before I go to the CHP, let me just talk about hydrogen. Yes, hydrogen, that's why I said a lot of hydrogen technology is still in the what's it called? It's still under development. It is quite expensive right now, but a little more of it now the cost is actually reducing, to be honest. Now, like I said, my research currently is on using what's it called nuclear heat for hydrogen production. And also, based on my own personal research in my master's degree, currently hydrogen generation systems are economically competitive with battery systems if you use the right technology, specifically high temperature hydrogen systems like the solid oxide electrolyzers and solid oxide fuel cells. They are economically competitive with batteries now. But then the technology hasn't gotten that much to commercialization stage. There are several hydrogen projects going on. There is one in Australia, I know one in Sweden, and one in the UAE currently going on to develop these technologies at large scale. Also here in the US, I think the 9 Mile Point nuclear power system has been integrated with hydrogen generation system. It's managed by Constellation Energy. So they use solid oxide electrolyzers for hydrogen generation with nuclear energy. So it's no longer too costly as it used to be, but definitely the cost can still reduce. Yes, you need another electricity source. I mean, that's the whole idea, right? We want to convert electricity to hydrogen. So that's the whole idea behind hydrogen generation. So hydrogen is not really a source of energy in itself. It's like a medium of energy. You use it to convert energy from one source to the other. So yes, of course you need electricity, and that's the whole idea. So you convert electricity to hydrogen and hydrogen back to electricity. I hope that answers your question about hydrogen and battery. I think this is unsustainable economic grounds utilize some of money there. Yes. So CCS, carbon capture. Oh yes, carbon capture is currently it's not currently not economically sustainable. That's right. We can't actually pay for it yet. But then initiatives are currently going on to make CCS sustainable. One of the ones I know that have been up for a while, especially in Europe, is they make people pay for carbon generation. So there's something called carbon credits and carbon taxes. So if you have a power system or an industrial system that gives off CO2, you pay for that CO2 generated. So when you make people pay for the CO2 generated, then you can make carbon capture economically attractive for investors. So if you calculate the amount you pay on CO2 per year, and you calculate the cost of operating a carbon capture store and storage system, and you say, oh boy, I don't think this makes more sense to just pay money. I mean, and because you get carbon credit for CO2 not released to the atmosphere, that's money saved. Then also you get to, have this, what do they call it? There's this community thing they say for companies where you show the community you care a lot about them, and that way you can prove that, you can show that you care about the community, and that improves your rating in the community as well, community acceptance. So that's also some of the ways we are trying to make CCS attractive, but in its actual self, CCS is not economically attractive. So back to CHP systems. CHP, as I said, you can generate both heat and electricity. So like this gas turbine here, it converts the energy in this fuel or biogas to electricity through the turbine and sent to the generator. Then the remaining heat from the system is sent to this waste heat recovery system, and that is used for heat in other parts of the integrated energy system. So that's the whole idea behind CHP. You have a system that you can use for both heat and electricity generation. The reason why what makes CHP attractive is that it improves the efficiency of the system by a very, very, very large magnitude. Sometimes it goes as far as doubling the efficiency of the system. So it's actually what everybody's using now. It's like the holy grail in heat to electricity conversion. CHP systems, they are the best. So this system description, the multi-generation I was trying to explain here. So we have the heat source and also the electricity. So we have two sources here. We have heat and electricity. Electricity could be from solar and turbines, and then we have storage in the grid, storage in electric vehicles, and then the heat is from this gas. So you could actually use a boiler to just fire the thing and get all the heat out from it. Have really high efficiencies in boilers, 60 to 70%. Then using this absorber chiller or heat exchangers, you can actually generate heat or cooling. So one very interesting technology that I think people should look a lot into are this absorber technology. So imagine you take heat, you take hot and generate cold temperature. Like, how does that happen? It's actually a very, very interesting thing. I've been trying to look into it for a while now, but I have other things. But I think if you're interested in the energy, if you're interested in studying energy, maybe at PhD or MSc level, or maybe your bachelor's level, I'll definitely recommend looking into these absorber chiller systems. They are very, very interesting system. A lot still can be done in improving them, and I believe it's going to be a lot of money. So I'll come to the questions. Let me just finish this system. So this system, basically, like I said, we have several sources and we have several users. So we have electrical and thermal sources, and we have electrical, thermal, and cooling users. So what I'm trying to state by giving the system is to let you understand how the systems can work together, how you can use one source of electricity or one source of power to generate several sources for other users, which is the whole idea of having integrated energy systems. And also, how does clean energy sources fit into this narrative? That's what I've been trying to explain here. So I hope I've been able to, give some ideas into how you can combine the systems together, generate electrical, thermal, cooling, hydrogen, and light. So like I said, I'm only giving high-level information here because when we go into these systems, I can spend a whole day just describing the system alone. So a lot still needs to be said, but for the sake of this, just to provide information, I think this should suffice to anyone that might be interested in this. If you have questions, definitely I'll do my best to provide answers to the questions. So someone asked, how can these integrated energy systems be applied in Nigeria? I mean, it's not even a Nigeria thing now. You can apply it literally everywhere. So one thing in developing energy systems, as someone that has been in this field for a while, one thing I will tell you is if you don't have people that want to use it, you don't develop it. If you don't have people you want to sell it to, you don't go into it. So the first thing is you have to identify your users. How can they be applied? I mean, think of this power plant in Lagos. What's it called? I've forgotten the name of the famous power plant in Lagos. I think it is a typical system that can be used for combined heat and power. So thank you, Egmi power plant in Lagos. You can definitely use for. So think of this system we have here. This is like a typical Egmi power plant. We don't have this what's it called? Solar and wind power and sources in Egmi. But every other thing you have here, you can definitely have it. You can have waste recovery. It's powered by natural gas. So, and it's connected to the grid. There may be people don't use electric vehicles. You move these two, and then you still have this whole system where you can generate heat, cooling, and electrical from just one Egmi power plant. So that's typically an easy way to apply them in Nigeria. Is the application of hydrogen energy storage economically feasible in the residential sector? Well, first thing, for safety, I wouldn't advise a residential person to do a hydrogen storage because in the gaseous form, you have to store hydrogen at very high temperatures, very high pressure, sorry, very, very high pressure. So any accident scenario there, it's a disaster. So you don't want that for one. And also, if you want to store it at low pressure, which is in a liquid storage, it is very, very, very cold. I'm talking of minus 200 degrees cold. So your hand touches it, that hand is dead. So I would personally, but economical feasibility, definitely, but from my own study, it is not economically feasible for residential sector because of the scale at which you need. It's very, very small scale. But now I believe there are hydrogen-powered vehicles. There are some cars that run on hydrogen now. There is one by Toyota, and also some Chinese manufacturers have some cars running on hydrogen. So, but they are scale because of cars, but they are very expensive cars, actually. Very, very expensive cars. But for residential, just to power your home, it's currently, from my own personal studies, it's not yet economically feasible. But maybe over time it will get there if we find more safe ways of storing and cheaper ways of converting this hydrogen. We'll talk about this later, Mr. Adeyemi Daniel. So we'll talk about this. We will deviate from the topic if we go into this. So this is a multi-generation example of integrated energy systems. And now to my own field, what I've been working on, nuclear powered integrated energy system. So here we have a nuclear power plant and you have biomass systems. The nuclear power plant, as we know, all it produces heat, very, very high heat, like 287 degrees. So, sorry. Okay, so nuclear energy produces thermal energy as nuclear power plant. Sorry, nuclear power plant is used to produce thermal energy, and what we use nuclear power plant for currently is just this thermal energy for electricity and sent to the grid. That's all. But now in an integrated system context, look at how far we can go. So rather than just going through this one single line to the grid, you can use some of the heat in this guy for biomass systems, or then from the biomass systems, you can generate heat and electricity sent to the grid. You can add hydrogen production. This is what I'm currently doing, adding this hydrogen production. But interestingly, I'm not even using the electricity for my hydrogen. I'm using this steam itself. That's what I'm using in my hydrogen. So that to let you know, even after this electricity, you can even from here connect to the hydrogen production plant and still have this highly resilient, closely knit integrated energy systems. Then, of course, you store the energy in batteries. You could have thermal storage, and of course, maybe heat engines. So I'm just trying to show you how you can converge or how you can integrate energy systems together, make one system give you several several sort of application for this energy system. So you don't need to have like 1 million sources. Oh, nuclear radiation. Okay, let me toot my own horse a little bit here. Nuclear radiation is a very interesting thing. Before I started studying nuclear energy myself, I always, stress myself about nuclear radiation and the likes. But then the level of safety in nuclear power plants to prevent radiation is the highest level of safety for any system in the world today. The nuclear power plants are safer than your aeroplanes. And in case you don't know, you have a higher chance of dying in your car than in an airplane accident. So that is how much you should know how safe it is to run an airplane. Now think of something that is safer than that. That's a nuclear power plant. So radiation is actually, if you are a nuclear engineer, you would definitely not care about radiation because the chance of it happening is 1 in 10,000 years. You have the chance of having radiation leak once in 10,000 years. That's like almost impossible to happen because power plants typically have 20 to 50 years of lifespan. So before, and also if you check the history sides of maybe Hiroshima and Nagasaki, which was actually a man-made accident, Then probably the failures of power plants are probably due to Chernobyl and what's the other one? So what I'm trying to say is, and look at the amount of nuclear power plants we have in operation today, and look at the number of accidents we have till date in history. It's almost insignificant compared to the whole thing. So radiation is actually not a challenge or not a concern for nuclear engineers in nuclear power plants. Hydrogen storage as a coupling point for power and heating systems. Let me see if I understand your question. So hydrogen storage, hydrogen is a storage system, right? It is energy storage medium. So you basically convert electricity to hydrogen. Then that hydrogen can be converted back to electricity for whatever you want to use it for. So coupling point for power and heat system. Okay, I think I get it now. So hydrogen systems, depending on the technology you use, they produce both heat and electricity. In solid oxide cells, the one I work on, the system operates at temperatures of about 800 degrees centigrade up to 1,000 degrees centigrade. So that is a lot of high temperature. And then the hydrogen produced has to be cooled down. So when you cool that hydrogen down, the heat you produce there, that is heat you can use for other applications. The same way when you convert that hydrogen back to electricity, you have a lot, because hydrogen there's a lot of energy in hydrogen itself. I think it has probably the highest amount of joules per kilogram among all four, probably, if not. So there is a lot of energy, and most of this energy, when converted from one form to the other, are released as thermal energy. So that thermal energy released can actually be used for secondary uses, for heat uses and the likes. And of course, when you want hydrogen in fuel cells, automatically, like it or not, you generate electricity. That's a point of electricity generation. And of course, the temperature of operation itself is high, so you can extract that heat for thermal purposes. So it's like in its nature itself, there's heat in hydrogen. Like most energy systems, actually, from my own personal study, I realized most of our energy exists in form of heat. When you drive a car, for example, the car moves, you burn your fuel in the internal combustion engine, a lot of heat is generated. When you press on the brakes of your car, heat is generated there due to friction and some energy wastage. So now you have regenerative braking in cars. You have some cars that are trying to extract that thermal energy for whatever purposes inside the car. Think of that energy conversion system. Almost everything has heat. Even your electricity to electricity conversion, where you have why do you think your laptop gets hot? Why do you think your TV gets hot? That's because there's a lot of heat energy just, moving around, wasting all over the place. And this energy can always be used. So the same thing in hydrogen production, but the thing in hydrogen is it depends on the technology you are using. If you use PEM fuel cells, for example, the proton exchange membrane, they work at temperatures of about 80 degrees C, so not so hot, but you can still get enough heat for domestic heating and hot water use, but not enough for, high use like industrials and stuff like that. So that's how hydrogen works as a coupling point for power and heating system. In the conversion of hydrogen itself, heat is generated, and of course, electricity is used during the whole process. I hope that answers your question. So this is it about thermal nuclear powered integrated energy storage. So far I've showed very simple systems where you just have, a few components coming together and so. So I want to just give one unnecessarily very complex system. And this is what it actually looks like in an actual setting if you actually want to do it. The way it actually looks like, I'll talk about sharing the slide later. The way it actually looks like in the actual system. So now see this. This is an integrated energy ecosystem, and there's no heat here. So just electricity. Now think of this. What we are just doing is electricity and gas, or maybe hydrogen, or maybe same gas. So let me see if I can go through this, if we can go through this together. We have wind and solar sources for electricity generation. We have natural gas or biomass systems. we have hydropower systems, we have where's the nuclear system? Yeah, we have the nuclear system here. These are our generators producing electricity. Then what are our storage options? We have the compressed air energy storage, which compresses air literally. You store energy by compressing the air and storing it anywhere you want, maybe underground caverns, in pressurized tanks and the likes. We have thermal storage, battery storage, and then of course, you can't have this system without carbon capture. So this carbon, so the CCUS Shalom was talking about, this is what it looks like. You capture the carbon from the atmosphere and you store it underground. So it's not like you don't use the carbon for anything. Maybe you can use it for production for some synthetic fuel production, but most of the carbon is stored. So you have the CO2 capture system sending to the storage. You have CO2 from the gas plant, you store them. CO2 from cement production, you store it. The only way you can use the CO2 is to produce synthetic gas. So think of how complicated it is just to operate the system. And this is the biggest challenge in integrated energy systems, the complication that comes with it, because you have a lot of things going on. And that's why a lot of people are not going into it. It's just a lot of work. So you want to do this, you have to study it for a lot of years. You need a lot of data to ensure you have a resilient system, because a lot of things go into play. So this same system is serving aviation sector, it's serving ground transportation, it's serving industrial operations, it's serving electrical users like the hospitals and the likes. And also we have hydrogen storage. Why didn't I mention that? You have hydrogen by electrolysis, and so it's just really, really, really complicated system in itself. And that is where the work is currently for integrated energy system. So I would advise, if this is something that interests you, and I think it should interest anybody interested in clean energy, because you can't have a clean energy system without being integrated. Because of what? The inherent problem in clean energy is that it is not always available. Your solar is not always available, your wind is not always available. So you need to add other systems to help you keep the system operating at all times. Otherwise, nobody will buy your solar or wind electricity. Imagine I want power at 2 a.m. in the night, and because my solar panel is not working, I can't get power. Who wants that? Nobody wants that. So you need storage systems for that. I mean, so many things. So moving forward, I will give these two examples of an actual systems working, just to let you know that, of course, it is complicated. Of course, it might be expensive, but some people are actually putting a lot of work into ensuring these things work. So University of California, San Diego, they have a microgrid. The microgrid is just a smaller grid. I believe everybody knows what a microgrid is. You have a smaller grid serving a very localized community, like a university. You generate all your energy, you store all your energy, and you control everything by yourself without dependence on the national grid. Another one is a district energy in Malmö, Sweden. The Europeans are the champions of integrated energy systems, like it or not, because I think the Europeans, they like to try things a lot. But here in the US, we want to test. So a lot of systems we have here in the US are probably in the universities and maybe some small research institutions or some national labs, where we keep testing to see, will the people accept this or not? Will it work? But in Europe, they just try, okay, 1, 2 tests, oh, that works, let's send it out. Everybody starts using it, then they learn on the job, which I think is better if you ask me. So in Malmö, we have, their own is more advanced or more complicated than what they have in UC San Diego, because they include both electricity and heat in Malmö. They have biogas, they have geothermal energy. Geothermal energy is also something that I really like, but I can't really talk much about that here. So what I'm trying to say is, these things work. These things are being used. People are actually looking into these things, and you definitely want to explore it if you are an energy enthusiast, if you are a clean energy enthusiast, if you are interested in renewable energies. You have to at least know what integrated energy systems are like. So that's it on integrated energy systems, how they work, how they combine, and how things work together. Wow, I've spent so long a time. I'll just round up. I'm sorry, I just realized I've spent almost an hour talking. Sorry. So the challenges of the system. So what are the problems we're having? Like I said, renewable sources, they are not stable. And these systems are very, very, very expensive. And because we don't have much knowledge on them, we don't know how long it will take to pay back. So the economics is a problem, and the technology itself is also a problem. So they are complex technologies. We don't really have much experience on it. So that is a problem. And also they are quite expensive. And of course, we need the government to support them. Those are challenges we are facing. How do we plan to fix this? What are our intentions on fixing this? Improve technology, of course. Let's get technology to an advanced level where we can actually implement the system. That is where I come in. We work on the technology. We try to see how can we improve the systems to make sure they are resilient, to make sure they are reliable, to make sure they improve efficiency and stuff. And then the government can come in by giving us money, provide financial incentive and support mechanisms to make this work, then the partnership between public and private institutions and other things like that. So yeah, I'm going to have to rush the remaining part because I've spent so much time. So policies that the government could do to support this is to provide, as I said, provide financial incentives, then regulations based on the performance. So if you have a system that works well, provide regulations to improve the system. You support R&Ds like they are doing to us, and then other things like that, feed-in tariffs, net metering, emissions trading schemes, that for the carbon capture thing, where you pay for CO2 that is emitted and stuff like that. So what does our future look like? This is the future in integrated energy systems. You need distributed resources, grid modernization. Like I said from the beginning, these systems are getting old, and we have to, bring new ones. So they're getting old, they're getting inefficient. We have to modernize our grid, integrate renewable sources, add artificial. I mean, everything gets better with AI, right? Add artificial intelligence, electrify transportation, demand side management, energy efficiency. These are the things we are looking at for the future of these systems. If we can sort this, I believe we will be fine. And so to conclude my whole talk today, we know that we have to transition to clean and renewable energy sources if we want to fight climate change. Integrated systems will definitely support and advance the Clean Energy Future Initiative. We need to combine heat and electricity, and we definitely need smart grids to enable integrated systems, because just one guy is not enough to do it. Then, of course, we need the support of the government, policy and regulatory framework. So as an energy person, you don't have to always deal with technology as well. You guys can go into government and, enable these things, because nothing makes any technology work faster than the government being in support of it. And of course, we know that from what I've said, I've tried to explain to everyone that adopting integrated energy system will help accelerate economic development of underdeveloped and developing nations. With these few points of mine, I hope I've been able to convince and not confuse you that integrated energy systems are the enablers, or is the powerhouse of the clean energy future. Thank you for listening, and I appreciate your time. If you have any questions or further questions, I'll be able to take them now. Thank you. Okay, so regarding the slides, so I can share my slides, I don't mind, it's not a big deal. But the problem is this: in academia, we have something we call plagiarism. So a lot of the images I have here are not mine. So what will happen is I will share the slide, but I will remove my name, so it won't seem as if I'm trying to claim other people's work, but I'll definitely send the slides. So that's just. So yeah, Mr. Victory or Miss Victory, I don't know. Please go ahead with your question. Thank you.
All right.
Winner.
Yeah, good day. Thank you so much for your presentation. It was quite insightful. Okay, so I'm very much interested in energy storage system.
Okay.
So I want to know, how complicated are the energy storage controls that are available now? How complicated are they? And how much of a risk can we, assume from thermal energy storage?
Okay, thank you. Sadly, I'm not really into control, so I can't give a definitive information on how complicated the control is. So it's difficult for me to tell you anything definitive because I'm not a control guy. It's a very specific aspect of energy systems control. That's what some people do, base their whole life on. So me coming here to just give a random information would be a disservice to those guys. However, the controls definitely could be highly complicated in the sense that, for thermal energy storage, you have to control the level of the fuel level, you have to control the temperature of the storage, and also you have to control the amount of energy being sent out. So it's a lot of, I wish I could, I have this thing I'm actually working on, not really fully control, but to see how the demand side and the storage side actually works together. So on the demand side, you have required temperature and a required amount of flow, maybe like flow rate. But in the storage side, what you only have is the liquid level and the temperature. So if the temperature in the demand side is lower than the temperature in the storage, but then there's a specific mass flow that they require at the demand side. So you have to balance your flow rate from the storage side and temperature from storage side to the temperature and required flow rate at the demand side. So it's a lot of mathematics and equations going on into that. But then it's fairly complicated, but the level of complication, I cannot say right now, but it is fairly complicated.
All right, thank you very much. Yeah, I'll try to research more on that. Thank you. All the same. Your presentation was quite great. Thank you very much.
Thank you.
And I would need your slides.
Yeah, I'll send them to Shalom. As I said, I'll remove my name because it's not 100% mine, so I don't want to claim someone else's work. I'll remove my name and I'll send them to Shalom.
All right. Thank you so much.
All right.
Wow. I don't even know what to say. Are there other questions? I think there was this kind of out of the scope question from Adeyemi.
Oh, okay. Yes.
Yeah.
Okay. Thank you for reminding me. I'm getting everybody different characters. Okay. Okay. Yeah. So, like I like to tell people that ask me about career in the energy sector. The energy sector is broad, like really, really, really big. You cannot finish it. So the most important thing is at your set-off point, when you start, you have to ask yourself, what do I want to do? Do I want to work on energy generation? Do I want to work on energy storage? Do I want to work on the control of energy systems? Do I want to work on economic viability of energy systems? Do I want to work on efficiency improvement in energy system? You have to choose your area. You have to choose your area. So when you know where you want to work on, then you can be able to determine. But if you just say, I want to work in any sector, you are entering an ocean and looking for a pin. So it's almost impossible. But there's a lot of things to do. But one advantage of not being specific is that you give yourself a higher chance of getting into the sector itself. So there's, okay, yeah, Deyemi, you can go ahead and ask. I think you want to ask in person. Yes.
Good evening, sir. Good evening, everyone. Thank you so much for this awesome lecture, and I really, really appreciate. The thing is, I've always had passion about the energy industry for quite a while, and then we have renewable energy, we have this, we have that, and all of that. So sometimes when you don't know where you're going, you tend to lose your direction or your focus along the line. So now you mentioned cases of where, because this is the first time I'll be hearing that anyway, and that was one of the reasons why I had to call you back. You mentioned cases where am I going to be working in the energy generation sector, energy storage, and some I mentioned and others like that. It looks a bit bogus now, but I can pick that energy storage and generation. I can really recall that easily. So I don't know if I can send you a private message and we can discuss further. And I don't know.
Yeah, that's fine. That's fine. I'm always open to, helping anyone break into the sector. So you have my email on the slide. You can just send me an email, and yeah, we can start our conversation from there. Yeah.
Okay, sir. On which site, sir?
On the slide, if you have the slide, my email is on the current slide, agbajm@rpi.edu.
Okay,
Or let me,
sir.
I'll type it in the chat.
Okay, the current slide. Let me just screenshot that. Okay,
Okay.
I've seen that.
Yeah.
All right, sir. I'm going to send you a mail. Thank you very much, sir.
That's fine. Yes, thank you.
All right, thank you so much, sir. Yes, sir.
Yep.
Thank you. And to Miss Shalom, thank you so much for putting this together. Some of us are out there that are really finding ways. Thank you for putting up this initiative. I've recently been so serious on that renewal, but then to a large extent, I'm grateful you put up those events and projects. Thank you so much.
Oh, you're most welcome. I mean, this is going to be something we're going to be doing every month. So I'm looking forward to everything that I'm going to also learn, because I'm learning new things too. I don't know if there are any other questions, please, while we are rounding up. I mean, it was such an informative section. The first time I heard from Mr. Muiz, I was very, very impressed with the presentation slides and everything. I was like, no, we have to share this with everybody. I have to share this with everybody. So I'm really, really, really glad that this came out perfect, more perfect than I envisioned. So are there any other questions? And I think we'll be wrapping up from here. So we'll not keep like waiting too much. Any other questions? We can just you can just unmute, or if you have maybe further questions, you can always send to me. Let me check again. Through any of can send to me on LinkedIn, you can send to me anywhere. Winner, do you have a question?
Okay, ma, good afternoon, ma.
Okay.
I don't have a question, but I just want to, I don't know if I can just make a request for us to, kind of drop our LinkedIn profile so that we can connect with each other, since we all have similar interests. It would be nice, connecting with each and every one of us here.
Okay, I mean, that's perfect. We can go ahead and do that. And then while we are doing that, can we briefly turn on our cameras just for a quick picture, just to commemorate the event? So if you are in a place where you can turn on your camera, please do us the honors to see your pretty, handsome, lovely faces. And while we go ahead to just grab our LinkedIn, let me grab that as well. While we'll go ahead to grab our LinkedIn information, can just quickly turn on our cameras. Oh my. Wow, I'm seeing. Thank you so much for joining. Thank you so much for joining. Thank you. So I'll be putting my own LinkedIn too, in case if anyone wants to connect. Oh, thank you so much. Okay, so what should we use? Which one should we use? Renewable energy, clean energy. What are we going to say? Clean energy, right? Since we dealt more on general clean energy. And then I even wanted to clarify, is there a difference between clean energy and renewable energy? I know that I get that question a lot.
Well, I would say there is. I mean, renewable energy does not necessarily mean clean energy. Yeah, it doesn't necessarily mean, but they are, in the current age that we are, or in the current context of energy system, they are sort of interchangeable. So, yeah.
Okay. Oh, sorry. Please let's not turn off our cameras. I know I hesitated. I'll just take the picture right away. Please let's turn on like our cameras. So it just, at the count of 3, we just shout clean energy and we take the picture. So 1, 2, 3, clean energy. Oh, thank you so much. I see everyone's beautiful smiles. Thank you so much. I'm taking much more pictures for anyone that still wants to turn on their cameras. Thank you. Thank you. Thank you so much for joining. I'm so glad that we were able to join. And this ends the first edition of the Renew Education. As I said, all the slide, as our instructor has mentioned, once he sends it to me, I'll just send it to all the email addresses. The email address that you registered with, just expect that slide there, and also expect the recording of this section there. And this will also be uploaded on our YouTube channel. So in case you've not followed us, please do follow us at Renew What Technologies. All of those information will be sent to you via email. And with the clean energy scheme, you'll be hearing further about that at our next edition. So communications will be sent across to us for the next edition in February. So thank you so much for joining once again. Do have a nice day. All right, bye.
Bye, everyone. Have a good
Thank you,
day.
Dr. Muiz. Thank you so much.
Thank you so much.
so
Thank
much.
you for having me.
Thank you.
Thank you.
Bye,
Thank you,
guys.
everyone. Thank you, Victor.
guys.
Thank you, Jonathan. Bye. Bye, 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 bye. Thank you.
Thank you.
Thank you, ma'am. Thank you. All right.
Thank you.
Thank you. Thank you. And I'll go ahead to end the section.